Good. Okay, so the title of my talk was using MOM6, and so this is kind of a rather ambiguous and could be a completely open-ended talk. I decided to interpret it in a particular way, but first I just need to acknowledge that there are a lot of people who've been working on MOM6 on the GFDL side as well as outside, and in particular, just acknowledge that most of these people have actually contributed some way to the contents of what we're going to talk about today. So MOM6, using MOM6, I think the right way of asking what that means is, where should somebody start if they're coming to MOM6 anew? And so I'm going to give you sort of some starting points, pointers as to where you should go if you're going to come to MOM6 afresh. There's one challenge with a sort of answering questions like this is, everyone's use of a model, every application is unique. Sometimes you have to write some special code just to do the problem you want. And so answering all questions in one, finding a generic answer to this question is actually impossible. It's always going to have to be a case-by-case basis. And there's a sort of some advice that I think modelers have learned over the years, which is extremely important, which is that if you're ever going to start building your own configuration or using a model in a new way, it's always best to start from something that's actually already working. So start with a working example and then evolve it, tweak it around until it's looking the way you want it, to reconfigure the way you want it. So that you don't, so you have a sort of a starting point that you don't start cold and end up in digging a very deep trench that you can't get out of. So to that end, I'm going to give you a quick run through of how a new user might come at this. And I'm going to give this from the perspective of sort of the ocean-only GFDL point of view, because CSM is something that the CSM folks will handle. Using models in the CSM context is something that NCAR is going to present later in the series, or is in charge of. So just briefly, I'm going to just quickly talk about how to get the code, how to use the code in terms of controlling it and looking at it. And I'll give a few examples of as good places to start, which are somewhat well documented, better than no documentation at least. And then just a few final comments on how things are setting up and how they work from an open source point of view. So quickly, I'm not going to go into much detail here because there is actually a MOM6 Wiki for users who are just building the ocean-only code. MOM6 examples wiki is a user-driven wiki page. It has instructions for cloning, which means obtaining the code, compiling and running. Running codes these days is pretty straightforward if you're using MPI. And if you just search for MOM6 Wiki on Google, it will be the first link if you don't want to write down that URL. And because this is user contributed documentation, it has, in my experience, my observations, the documentation is pretty complete and up to date. Basically, people were able to follow through the steps as outlined in the wiki, and it generally works. We get very few questions about how to actually build the model on someone else's platform. And to that end, I think it does actually suggest that the code is portable, and that somewhat depends on FMS, the underlying infrastructure being a portable system. So as I said, I'm going to give something which is not about how to use the model in the context of CSM. So I'm not going to talk about workflows or anything specific to workflows, including our own workflow at GFDL. And I will also suggest that when you're starting out, it's much, much easier to start out if you're working with an ocean-only configuration, because ocean-only means only using MOM6 code. The moment you start getting into coupled configurations, and even isocean is strictly speaking coupled, then it involves other codes and couplers, and it's a lot harder. So if you're starting afresh, start ocean-only. To that end, though, however, when it comes to global modeling, it's pretty hard to do global modeling without an ISO model. So you're kind of forced to think about couple models when you start talking global. The instructions are, for the most part, targeted at people who have some experience with modeling, meaning that they have some experience with Linux as well. And it's been an interesting question whether more documentation is needed to get, say, a graduate student who's just arrived with no Linux experience up and running. It's something which I'm kind of hoping that maybe another community might feel is something that they will invest in terms of that level of documentation. But for the time being, this user-driven installation documentation seems to be working very well for the group of users we have. So controlling MOM in MOM, the very first thing that you need to know is how to get parameters in and out of the model. And we have we have our own parameter syntax, which is a simple key value pair system. For example, KH, which here is the horizontal Laplacian viscosity, is simply set to 25 meters squared per second. The input is via a set of files which are bootstrapped. You list the list of parameter files in a file called parameter called parameter file name, which goes into a hard-coded static file called input NML. And that's a bootstrapping mechanism because somehow you have to get MOM to be able to find out where to find the parameters. But then in this parameter file name on the right-hand side, you can list any number of files of your own choosing. And as by convention that we use the names MOM input and MOM override, as I'll explain in a moment, it's purely a convention. You can call those whatever you like. If you want to call them Fred and Joe, you can call them Fred and Joe. So once you've bootstrapped and you've got your parameters into this thing, into these files, and those files are listed, the model will read them, and they'll read them in a key value pair, and it will actually do some error checking on it. For example, we consider it an error if you specify the same parameter twice with different values. Things like that are things which are hard to trap in conventional Fortran name lists, which is one reason why we went down this path. But the other value of the system which we're using is that it actually is self-documenting. So when the model's finished reading all the parameters, it will then also log all the parameters that it read, and it will log it in several ways. It will log all parameters in a file called MOM6 absolutely everything is written down into that file. It will also write a shortened version of that parameter file, which is only the parameters which were not set to the default value. So if I can just draw your attention to the first lines of code on the top left here, on the middle left here. It says k equals 25, and then there's some comment symbols, and it has units and a default value, and the default value is 0. So these two lines will appear in the mom parameter.short file because it's non-standard, and it will also appear in the mom parameter.call. But if we'd set kh to 0, those lines would not be in the .short. So it allows you to have a much shorter overview of what the configuration of the model is. The fact that the units are reported is a very valuable aspect of our system. Because it means you have units for your parameters, and that's something which we're very keen on expanding in terms of our testing capabilities. You'll see that the API is very simple, and the API has the specification of what those units are in this Unix string, but it also has this scale parameter, and this is something that in Marshall's talk perhaps will explain what we're doing there. But basically, the model is able to test every single term for dimensional consistency. That's a very, very powerful advance we've made in the last year. So as I said, we have a convention of using file names MOM input and MOM override. It's it's become a very, very powerful convention. What we like to think of MOM input as being the sort of a canonical configuration for an experiment. And then if you want to run a perturbation experiment where you are going to change something to see whether there's, to check a sensitivity, for example, you would throw that change parameter in the MOM override. And there's a syntax for changing a parameter so that we don't have this problem of specifying the same parameter twice. We have this hash override syntax, and you throw the overrides into this separate file MOM override, and it lets you say, oh, this is, you can very quickly see that this is a perturbation from a baseline experiment. The model, of course, runs in parallel, and the parallelization is documented. The inputs can also be controlled from MOM input or whatever file you decide to put the parameters in, but they are documented in a separate file, MOM parameter.layout, because these parameters don't change the numerical solution. They change the format of the data inside the memory and perhaps in the files, but they do not change the actual result. So we consider these to be auxiliary parameters, which are there purely for computational reasons. And so the model can be decomposed. There is an optimal tile size. So a tile size is how many points you have on each processor or node. And there seems to be an optimum of somewhere between 12 and 30 by 30, depending on the chip that you're using. There is a halo in order to get the parallelization to work, and the halo can be somewhere between actually between 1 and 4. But typically, for most advection schemes that people choose to use, the higher order ones, you need a halo of 3 or 4. there is it is a requirement that the code bitwise reproduces across any layout. If that wasn't the case, then your results would depend on how many processes you chose to use, and that's not we don't consider that to be useful science. So one feature that catches people off guard is a great feature. There is no requirement that the tiles actually have the same size in each processor. So this means that even if you have a nominal global grid of say 128 by 64, you do not have to use a power of 2 number of processors to decompose the model. Using say you could use 6 processors, and then you'd need to have a 2 by 3 layout, and one of the processors would be something like 48, 48, 49, or whatever the numbers are to divide 128. So it's possible for this model to run with different tile sizes, and it sorts itself out so that it throws away the redundant columns as needed on some processors. So that means that you can use any number of cores you like within reason. Their only limitation is that you must have a wide enough tile for it to fit the halo, so that you're not your halo doesn't go over to the second processor across the boundary. I can't see my slides because my own window's there. Sorry. Okay, so restarts. So just like parallel decomposition is required for models to be able to restart across some time boundary, and that's because many jobs can't fit into a single job submission. And if you had a non-bitwise reproducibility across a restart boundary, then of course your results again would would depend on how you decided to run the model. So that's a requirement that we have bitwise reproducibility. And it's worth noting that here there's a certain procedure protocol for where stuff lives. This is actually controlled by this bootstrap file, this MOM input NML, this Fortran name lists. These output directory and restart input directories and so on are, again, it's a convention that it is configurable, and I don't actually know if CSM's using our convention or something else different. But for the most part, we take all of our inputs are read from the input directory. All diagnostics are generally written in the local working directory, and the restart files are written into a separate directory, restart, so that you have to copy the files from the restart to the input if you want to start the next segment. That's a convention we use. Again, it's configurable. It's a good convention, I think, because it means that you can repeat a segment without making a mistake if you simply don't move the restart files over into input. So diagnostics, we'll talk a bit more about this later, but the diagnostics are using the FMS Diag Manager, which when I arrived at GFDL, I was actually very impressed with. It's a very powerful diagnostics utility. It's controlled by a file called diag table, and that seems to be a hard-coded file name. And it has 2 segments in the file. It has a beginning segment where you define files. And so here I'm showing some files called Ocean Daily, Ocean Monthly, Ocean Month Snap, Ocean Annual Z, and so on. And you specify in these files frequencies of output. So these are going to be the frequency for either a snapshot or a time average. And then lower down, you list the variables and you specify, you associate a variable with a file, and a variable can be associated with many files. So for example, I'm showing theta O, which is the ocean 3-dimensional temperature, using the CMIP the IPCC naming conventions. And here we're showing ocean model, which is taking TS, temperature in 3D, and writing an annual time average. Mean means time average, and that's being put in at single precision. I think that's what the comma 2 means, into this file, which is defined by the ocean annual up at the top. There is other modules. There's an ocean model underscore Z. And this is a case where we are doing the taking advantage of the fact that MOM6 has all this remapping capability. So we are defining a Z coordinate, even if the model is not running in Z coordinates. And we're doing our diagnostics of this 3-dimensional temperature in a Z space, which is, in this case, happens to be the World Ocean Atlas vertical grid. And we are remapping, doing the time average in Z space here, and putting it into this file with an annual mean and a monthly mean. This Diag Manager is also capable of doing regional diagnostics, which I won't go into here, but there is documentation of this on the webpage already. And then one thing that we do with MOM is that rather than writing a static documentation file where you might say, oh, these are the diagnostics available in this model, which requires a maintenance of of that document file, whether it's a Word file or an HTML file. What we actually do is we have the model write a list of what diagnostics are actually available. And one reason we chose this is because the diagnostics are a function both of the configuration of the model, whether you are using general vertical coordinates or stack shallow water layer mode, but also because you can turn on all of these arbitrary coordinate diagnostics. You can do diagnostic in density space or diagnostic in z coordinates, and so the diagnostics that are available are simply a function of the model configuration and differ between experiments. And so what we do is every time you run the model, it generates a file called available diags, and that is a list of what the diagnostics are available. So if you want to find out, the best thing to do is run the model quickly in your configuration and then see what that file has in it. And that file, that documentation will have a list of all these variables with their meanings and units. Okay, so I want to quickly start talking. I want to talk about briefly talk about four actual configurations. And these configurations are part of the MOM6 examples repository, which we'll go into a bit more later. Just to quickly say that the MOM examples configuration, which is the repository which has that wiki page, was a repository that is sort of like a kind of a catch-all for everything that was happening at GFDL. We're actually rethinking the design of this repository layout, which I'll explain a bit later. But for the most part, it is, for the time being, where you can find examples of GFDL experiments. There are analogous repositories at NCAR and at Rutgers of cases that those respective institutions are developing. And in time, there will be kind of a network of many different places where you can find examples of configurations of MOM6. So our MOM6 examples repository is broken up into several directories associated with the kind of configuration. So I've hidden the coupled model configurations. I've exposed just a few of the ice ocean models because we're going to talk about one of those. But the ocean only directory is the one I wanted to have a full listing of, because three of the examples will come out of there. So you'll see these directories with the sort of configuration type, and then there is an SRC directory, and inside there are actually submodule links, Git submodules to the source code. And these are not the actual source code. If you just checked out this repository, they are effectively symbolic links, but they're using this Git submodule concept, which I will explain briefly later on. But this repository is a starting point, and the four experiments I want to go through are the double gyre wind experiment, the Phillips two-layer experiment, a flow down slope, and then a global ocean model for 05. So ocean only double gyre. So this is our I would say this is one of our simplest configurations, and it's something that dates back to Bob's thesis, and it's uses very small part of the model. It's basically stack shallow water. It is stack shallow water equations, and the reason we like people to try it is if this doesn't work, then something's wrong with your computer, because it's that simple. It's like the model doesn't use very much code. It's just integrating forward some momentum and continuity equations, and if this doesn't work, then you need to sort something out. And I don't know what would be going wrong, but for the most part, this does work. And so it's always a safety check that. So our first thing is, does double gyre work? Double gyre has a Jupyter notebook in it. I apologize for the rainbow color map. This is quite an old notebook. And this notebook is something that hopefully with a very small installation of Python, you would be able to up and run and check that you can actually do stuff with the model. So we use netcdf for the file for files, and this notebook just shows you how to read in some output from the model, and in fact in this case it animates it. We I am very much a fan of using Jupyter notebooks to illustrate and document procedures. However, I'm not in favor of advocating for one particular system of analysis. So this notebook is actually using SciPy for reading the files and just matplotlib. We will be adding other formats. I hope we already have notebooks that use NetCDF and Xarray, and I think we should be adding some more of those along with using Seaborn and a few other packages, just because people have different ways of working, they have their own favorites, and just having an example where somebody's favorite system is being used, I think will be very much more useful than actually saying this is the way you should be doing it. So double jar, as I said, is a very simple model, and it's kind of useful model because you can turn up the resolution and it starts doing interesting things. It starts eddying, and it's sort of textbook stuff in terms of what's going on in there. But it's only effectively I think it's a 4-layer stack shallow water model, whereas ocean only flow down slope is also a 2D model, but it's now X and Z in the XZ plane. And so this is an interesting one because it exposes the various choices in the vertical structure of the model. So whether you're using stack shallow water mode, a MICE-Ficknell mode, or one of these ALE driven coordinates, general coordinates. And there's a notebook in here also. I can't remember what system I'm using. I think it's NetCDF 4 for reading the data. But this notebook, I took the opportunity to explain how not to look at the vertical. It's really, it's quite a lengthy notebook, and if you'd be interested to see if anyone actually can follow it and make sense of it. But it's a notebook trying to explain how the model is actually storing data itself in memory, and therefore what it looks like in NetCDF files when you're both looking at what we call native format, the native storage, which is just the functions of IJK, or if you're writing it out in one of these diagnostic coordinates like Z coordinates. And the fact that the model is able to do vanished layers is something that can confuse people. When you write the model out and you have the ability for vanished layers, you basically always have data even if the layer thickness is 0. And this can confuse people because they're used to seeing data masked if you're a Z-coordinate modeler, for example. And this is not the case for our output in native space. And so when people start plotting the native data, they can start worrying that they haven't got the topography in their model or something like that. So this is a notebook trying to explain how the data is stored in the vertical and how to look at it. This is, so moving on to something more complex now. This is now a 3-dimensional model, the Phillips 2-layer test case, and it's a good one because it's a relatively affordable but 3-dimensional model, and it's been published a few times. The Phillips 2-layer model is a famous model used for looking at mesoscale instability. And Bob Hallberg most recently used this particular configuration in 2013 for his resolution function paper. And so I haven't got a notebook in there yet. All of the plots that Bob used in his paper were done in Ferret, and I think it would be a good exercise for some young person to see if they could reproduce Bob's plots, perhaps not using his color scales, but at least getting the results and figures looking the same, and then doing that in Python, hopefully. So this is a useful one because it's relatively recently documented, and the experiments should be exactly the same. The configuration that we have there should be one of these experiments exactly. And then finally, there is, if you wanted to start for looking at a global ocean model, there is no choice really but to consider an ice ocean model because the high latitudes need sea ice to have anything for the ocean to look at all realistic. And I would suggest that you look at the OM405 experiment in the ice ocean SIS2 directories. This is a half-degree global ice ocean model. It uses the GFDL SIS2 sea ice model and the GFDL coupler. That's because we are at GFDL and that's all we can support. That's not to say that it shouldn't be too much work if you have a working version of the MCT or the NeopSy caps, because they already exist as working couplers. Working with another sea ice model is something that NCAR is working, I think, at EMC as well. But something that is out of our domain in terms of being able to support it at this point. This particular model uses the GFDL vertical physics, and I highlight that because that is not KPP or using CVMix, but using our own physics packages. EPPL is this package that Steve mentioned in an answer earlier, I think to Joanne. And so this is it's worth highlighting here because when we decided to join forces with CSM and NCAR, it was decided that we would not be using the same physics for the sake of the science, so that we had some diversity in science. And so we're maintaining these packages to be able to have different physics. This configuration is non-eddying, it's coarse resolution in other words, but it's not as coarse as the 1-degree models that we would have been using, say, 8 years ago. It's a choice we made, and we are not yet clear whether we'll be supporting and publishing the coarser resolution versions of this model. Probably should, but we're not doing it yet. And then the model also uses GM and neutral diffusion parameterizations, which are necessary when you're not resolving the eddies or permitting the eddies. And so there's a curve down here that you'll recognize from Steve's talk, and just to prove that the model actually works. We're quite happy with this configuration. It's certainly, in terms of metrics, a good configuration in the series that GFDL has produced. So the reason for highlighting these four experiments is that they're either fairly very cheap or well documented, in the sense that there are papers about these configurations already. And so it's a good starting point because you've got something you know is being vetted. I'm afraid to say that there are many of these other experiments in here that are in many ways left over from our development exercises. You know, we would say, well, let's see what we can do with this. And so we'd create an experiment that might use some feature. And then the experiment sort of was added there as a way of testing the model, but not actually necessarily vetted as a good experiment as a starting point. And so when I say we want to redesign MOM6 examples, it's partly for that reason, that we need to actually break out what we should consider good tutorials and starting points of these experiments, and put the other ones actually into a testing repository that we'll use explicitly just for testing. And that's something we've just been discussing, and we'll announce and discuss, you know, with a larger audience when we've figured out how to do that properly. Okay, so about the repositories. So the MOM6 examples is what we call a super repository, and that's actually, because it has all these experiments in there, it can get quite confusing. If you are building your own experiment, you should take a repository point of view and say, I want to keep all of my stuff together. And so this is what we are advocating now, is to actually say, create a repository just for that one experiment, or at least that one configuration. And for example, we have one for OM4, the one we just described, for OM405, and the quarter degree version of it as well. And that experiment, that repository would contain everything you need for that repository. I'll highlight it here only because the reason that we've come up with this is it makes development really easy. Whilst we're currently in the midst of retuning this configuration, and the retuning process is exactly like developing code. You know, you have a main branch, and you might decide you want to try some Sense3 tests out, and so you can just literally create a branch, change the parameters in that branch, evolve it forward. What it does when you're using Git when you're applying these sort of software development tools to model configurations, it forces you to do good things like record what you're doing. It also makes everything reproducible and recoverable, and it's been a huge boon to our ability to figure out what we did when we were saying, oh, we saw this result before, what do we do? And it's all there in the Git logs. And so this is a way of organizing your life. We recommend it very highly, and we're going to try and break out, shall I say, the way that we're doing our development out of MOM6 examples, which is a big super repository right now. We're going to start isolating some of the experiments that we're continuing to develop and make those independent repositories. And so this is a view of how everything fits together right now. MOM6 examples is this big super repository. It points to particular versions of the code with these symbolic links, these Git submodules. NCAR cases, ESMG configs, all these other super repositories are very analogous. They point to their own versions of MOM6. And right now, those are collections of experiments for the most part. And we're advocating that we should actually think about breaking them up into smaller parts. This is a slide we've shown before about how everything's organized for those who need to understand it. Okay, I'm just going to quickly delve into the structure of the MOM source code briefly, because it's important for new users to have a clue of what's going on here. So there are several directories which have source code in them. The first is the config source directory, and in here you will find several subdirectories, of which there will be duplicates of code or code that doesn't seem to match anything to do with what you are interested in. This is code that is selectively compiled, and it depends on the context in which you're building the model. So for example, the NCAR coupled model needs to use the NeopSy driver and then has to choose a memory mode, either dynamic or dynamics metric. And so those two parts would actually be compiled, but it would be incompatible if you were to add in, say, one of the other drivers. Whereas to build the standalone model, you'd have to use the solo driver and then again choose either dynamic or dynamics metric. So this is the sort of driver level code, and what it does is this code is basically code that maps an API that's compatible with one of the higher level drivers at, say, NCAR or EMC with the interface that we have in MOM. So the idea is that MOM only has one API, and then this is like the layer that maps between our API and the coupler. There's a few other directions in there which I won't go into, but one in particular is the iShelf driver. But the solo driver is the one which most people would be looking at, and the instructions on the wiki for compiling are used solo driver. The next directory of interest is the PKG, and this directory is actually not compiled in place. This is a list of submodules which are essentially symbolic links to external packages. For example, CVMix or the TOS10 equation of state, GSW Fortran. So these are not compiled in place because often these packages have main programs or C code or other codes that just shouldn't be compiled with your model, and so we have to be able to selectively point to parts of those packages, and so we do that with symbolic links from the source directory. But this is where, if you have a package that is going to become part of MOM6 as a sort of library, this is where it would live. They have to be cloned. They have to be generally you would do a recursive clone of your super repository and get this would be obtained for you. But if you don't, if these directories are empty, it means you need to populate them with a submodule update. And just one last thing is the version that we are currently compatible with is recorded by Git as a submodule there. And that's important because it means that there's no one's requiring us to stay up to date, or vice versa, that the package can't evolve in order to maintain compatibility with MOM6. And then one of the most important directories, of course, is the SRC directory, which has the code that we actually integrate forward in MOM6. So this is the code that solves the equations of motion. It has all the code that does the diagnostics. Every file in this directory is compiled. There are some rules, there's some code styles to pay attention to. We don't use CPP macros except for memory and grid macros. We don't like CPP directives for the most part. There are a few that have managed to get in there, and we have been talking about trying to get rid of them. We will continue to try and do that. So there is a particular structure here, which I will go into in a bit more detail. So this is again SRC. So the directories are ALE, which has all the code to do with the vertical remapping, and this has been broken out from the core because it's reused in both diagnostics and in the dynamic core, and actually in the initialization. So the remapping tools are invoked in many different ways. So ALE is almost a standalone piece of software. The core has the dynamic core for the momentum, the code for integrating forward the momentum equations, continuity equations, not the tracers. Tracers are in their own directory. You can see that at the bottom. And so the tracer code is separated because it's generalized to be able to handle any number of tracers. The tracer advection and the parameterizations that act on tracers are all in that directory. The diagnostics is actually not all our diagnostics, but just a special group, set of diagnostics where certain things like budgets for momentum and so on are being diagnosed somewhat independently from the other equations. So for example, there's an energy budget diagnostic in there, where you can work out all the terms in the energy budget and so on. So those diagnostics live in the diagnostics directory. There's an equation of state. We have 5 equations of state. You get to choose which one you want. And so they're grouped out separately. And there's a single API that lives in there as well, which selects between the 5. And then perhaps an important one for people trying to build MOM6 into their own system is the framework directory. So the framework directory is really the interface to the lowest layer of software, which is in charge of communications and I/O. And right now we're using FMS. We will, at GFL, continue to use FMS. We like it very much. But the idea of the framework directory is that if you needed to do this, in principle, you could replace the calls to FMS with calls to your own infrastructure. No one's actually done this yet that I know of, but it is the case. We do let things slip occasionally, but for the most part, every call to the infrastructure is only from the framework directory. The idea here was looking forward. It might be that someday somebody has to actually use a different infrastructure, and so this was the idea here, was to try and make sure that was something we were not, but we make easier to happen. Initialization has stuff for initializing state and grids. And it's fairly self-explanatory. And then the parameterizations are broken up into 2 directories, lateral and vertical, for convenience. And then there's one last directory, user. So this is a directory that contains code that's specific to one configuration. So for example, the double gyre experiment has a double gyre wind, which is specific to that configuration, and there'll be some user code associated with that particular shape of wind forcing in that directory. That's the idea here, is if you've got something where you're adding something of your own for a particular experiment, you would add it here, which is why we call it user rather than something else. Now, there's 2 other directories in MOM6 which are really, really important. One of them is, for the most part, something you don't normally realize is there because it has a dot in front of it, called dot testing. And this dot testing directory contains the scripts and make files that are run by the Travis CI continuous integration system that happens when you send something to GitHub. So if you've enabled it on your fork and you've pushed some code up to your GitHub fork, Travis CI will run these tests and you'll get a check mark or a red X, depending on whether you've passed all of our tests. These tests are incredibly powerful and we are expanding them. In fact, there's a big pull request coming soon from Marshall Ward that will expand them even further. And in fact, this is where one of the tests which is being added most recently is a rotation test. But before that, we've added this dimensional testing capability. So this is something that's really important because it helps you know if code you've added is passing tests, and it helps us because it means that the code has been at least checked for sanity in that sense. But it's actually a directory that you can use for your own development. I mean, the experiments in here are not real experiments. They're tiny, tiny little tests. Some of them are unit tests, but they are something like 8 by 10 points. There's nothing physical about them. They're simply trying to exercise code. But if you want to figure out whether you've got some bugs, you can go in there and see if your code passes these tests. Perhaps the most important directory is the docs directory. And this is a work in progress by all means. There is a read the docs site, which currently points to a somewhat incomplete documentation. There is a work under development and work right now by Kate Hedstrom is a fuller documentation, which is actually the one I'm showing here. It's basically where we want to host all of the documentation for the model itself. So the equations, how all of the innards of the model work, and all of the APIs. That is what's going to be hosted on Read the Docs. NCARS has their own version of this already, and the idea is that in time this will become complete, that we will be able to actually just point people to here that this is where you can get started. Okay, so that's hopefully enough pointers as to how to get started, and I ended up here. It's my last slide, just to say there was more to come. You've already heard the Lagrange and remap discussion from Steve. Bob is going to talk about the equations and algorithms in a few weeks' time, and Marshall Ward is going to talk about some of the CI and that I was alluding to. And then later on, we've got talks from Raf and Matthew on analysis and ocean data assimilation. Thank you very much.
Wonderful. Thanks, Alistair. Let's see. That hands up from Santa. Go ahead and unmute yourself.
Hi, this is Santa. Thanks. Just a quick question, Alistair. And as time permitting, if you could expand, could you please tell us about the MCT driver and the other drivers like the dynamics and the dynamic symmetric, if we were to just bypass and use only
Okay,
those .h files in them?
So that directory, that config, I could bring up the slides again, but I'll just kind of assume you can remember it. The config sort directory has all of these drivers in it and a few other things. Dynamic and dynamic symmetric are not drivers. They are simply memory models. And so you have to choose between either I need a slide on this perhaps. That's what I should really do. There are two different ways of shaping arrays in MOM6. We refer to them as symmetric and non-symmetric. They don't change anything from the point of view of the solutions. They're just ways of making sure that there is data on the outside edge of a domain if you're working with open boundaries, for example. There is a static memory mode, which requires you to know when you compile what size memory you want. But for the most part, people aren't using that. But it is available and gets you a few % speed up if you care about that sort of thing. But those are the memory models. The drivers, MCT, NeoOpsy, the regular FMS coupler, and the Solo driver are the codes that are calling MOM6. Solo driver is obviously the Solo driver, the one you need if you aren't using a coupler. MCT is an earlier NCAR coupler, and I think I should perhaps defer to somebody at NCAR to comment on whether that's even still working or checked. Anyone?
It is, in fact, we're still using it actively because not all the components are NeoOpsy compliant at this point.
Okay, thank you.
We were first out of the gate with NeoOpsy, so.
Right. So NeoOpsy is still under development then, is that at NCAR?
That's correct, yeah.
Right.
For some components, yeah.
So would I be on the right path to imagine that the MCT driver at some stage when things are more mature would be obsolete?
MCT will become obsolete in the CESM world. I'm not sure about outside of CESM.
Okay, thanks.
Xiaoning?
Hi, thanks for sharing the examples. That's really helpful. I just have a really quick comment regarding what you mentioned at the very beginning on outreach. If you are trying to get a new grad student to get started on Unix, CSM has this, NCAR has this Unix tutorial that's part of the CSM starting pack. So I will post the link in the chat, and anyone who finds it helpful can use it.
Thanks, Xiaoning.
So I will say that one of the reasons that we got interested in working with NCAR and CSM is that NCAR promised that CSM would actually reach out to that community, which is to bring to help you all out.
Well, Xiaoning is a beginning graduate student, but a very capable one. Mostly got herself going. Okay, other questions for Alice?